My name is Noah Caulfield. I'm a senior at the Academy for the Technology and the Classics, and this is my third and final year in the Supercomputing Challenge.
My name is Dimitri Maligan-Voorhees. I'm a junior at Santa Fe High, and this is my first year competing.
Our project this year is ASL detection for real-world implementation. We just had a slide about who we are. So the goal of our project, we have three main aims. First off, we want to basically create a program where someone who knows sign language can move their hand in front of their computer or their consumer-based system, so whether it's a webcam or whatever, it's just a general thing that most people have, and the computer will recognize the ASL fingerspelling gesture, and then will tell the user what gesture that is. So basically like a translator, which there has been support in this in the past for like open source and just like small university projects, but there really aren't any widely available products or options for people who truly would rely on this type of software. There are options out there. I mean, there's like gesture tracking gloves for people who rely on sign language, but they're just astronomically expensive. Whereas something like this, it's just code. And if somebody has a computer, there you go. So for our project, since there's not a whole ton of preliminary programs already made, we just simply looked at any type of computer vision or gestural recognition technique, program, source, anything that might relate to what we want to do. Then, from all of those, we sorted through them, got valid ideas, or so we thought they were valid, of techniques or methods that might work, and then we designed two prototypes, compared them against each other, and then settled on one final project. So, as I said, we actually, once we were done sorting through all of our research, we had 11 different viable methods. That being said, some of them we just didn't know how to do, but they were still valid. Motion tracking and computer vision or graphic resources were also heavily relied on. A lot of our projects, or the methods that we looked at, were less about having to use the keyboard, but more just simply you click your icon or like compile and run the code, and then it would just immediately go into the project or the program, which is what our product does as well. Since Dimitri and I, we do not actually know sign language. I don't even personally know someone who relies on sign language. I really like computer vision, and actually, I had started this project by myself, and Dimitri had joined us in December. So a lot of our code and working, it's been a really odd process. But we have a product, so it's different. We worked with the New Mexico School for the Deaf, a volunteer, Arissa Baca, and we worked with her about sign language, fingerspelling, like the basics of fingerspelling, and how we could incorporate them into our project seamlessly so that someone who has been using this their whole life would be able to transition into using our project with minimal issues.
The big issue with ASL is that for communication, people don't rely on fingerspelling gestures. They generally use, there's a sign for almost every word, and that is significantly out of the scope of what we were trying to do. So the fingerspelling with only 26 gestures was significantly more accessible to us.
It truly served as a basis when we didn't have really a whole lot of previous work to go on, which made things a lot easier. Another thing to mention is for American Sign Language fingerspelling. As I said, there's 26 gestures, and then of course 1 through 9. For them, there's also, such as we may have like colloquializations or just like slang, ways we phrase things. For American Sign Language fingerspelling, they have the same thing. There's regional differences, which we should have thought about that, but there definitely are. And some of just the way people even just move their wrists to seamlessly transition through fingerspellings are completely different, whether I'm in Santa Fe, New Mexico, or New York City. So for our project, in working with the School of the Deaf, we chose to just work with our surrounding, the Santa Fe area, and just the standard rudimentary fingerspellings, because they truly are the basis where all the colloquializations come off of. So as we previously stated, we had two viable solutions discovered. The first one was a contour comparison technique. We completed this with the computer vision library OpenCV using Python, the computer language. Basically what it does is we'll have the user's web camera, so you initialize your program, user web camera pops up, and then you'll have the gestural space, or the region of interest for technical terms, will be shown in like a blue square, and that's where you do your finger spellings. Is just like people who actually rely on ASL, they have a gestural space around them where they generally don't move their arms outside of it. That area is that input we're converting to contour, to a static live contour feed, where then we have a pre-selected library of contour images of ASL gestures that we compiled ourselves with the help of the Santa Fe School for the Deaf. And then it compares the input to the gestures and then tells the output. For our second method, it's using the Xbox 360 Kinect's adapter. Hopefully one of you guys have seen it, maybe used it. 2011, it was actually the #1 sold adapter in America, so just everywhere. Reasons for choosing it is that it's a fantastic adapter. I own one. It truly had a lot of power to it, and we truly thought we could utilize it. And its main method of extraction and detection for ASL is that instead of being confined to sitting at a desk with the gestural space where you have to move your hands and anything outside of the gestural space is not recognized, using the Kinect, the user can be anywhere that the Kinect can see. Because what it's doing is basically it's selecting just the hand, it's then putting that into contour and like exporting it from the rest of the body, and then slimming it out so there's just an outline of a hand, and then graphing where the hand would be to make these certain gestures, which is really cool.
The beautiful thing about the Kinect is that it's not limited to one area. It's designed to track people in 3D space because it's used for gaming. If you're trying to play some tennis game, you're not going to be confined to standing in one area. So it's focused on mapping people in 3D locations. So as such, anywhere in the room that the Kinect can see, it's going to be mapping the depth of your room and where you are.
That being said, one of the complications with the Kinect is that since it's looking at just people or figures, it recognizes a person, instead of having detail to them, they're simply this type of blob figure. And whereas it might be able to detect like a wide movement, something like if I'm playing one of the games for the Kinect that would be recognized, something such as the like flick of a wrist or the change in my fingers, that type of thing is a lot harder to recognize. But we tried. So here's a screen capture of the Python contour comparison system. That screen capture is from our February presentation. And basically you have just your like raw data output, and that will tell you, yeah, that's cool. That will tell you basically margin of error. So if it's like close to 1, if it's not close to 1, or if it's 0, which is an exact copy. For running this program, we currently have 76% accuracy rate, but we only have 6 of the 26 gestures fully edited and working for the program. Because each gesture takes quite a while once you're like in Photoshop, editing it, and then testing it with the program, tweaking it, and optimizing the image itself to work with the program.
Because essentially what the program's doing is it's taking this box that it's converting to contour and it's comparing it to a library of contour images that we have. Essentially a pixel by pixel comparison saying how close to this set of images is this image and to which of those images is it the most similar. And that's how it determines what gesture you're doing.
Yeah, that's why an exact copy probably never going to happen. It'd just be really weird if one did. So,
Question?
of course.
Do you have just one baseline image for each gesture, or do you have several to match with?
We currently only have one baseline, but for our project, we have our website, asldetection.com. We're looking at having our project, our code, the research. Since we realized we didn't have all 26 gestures recognizable by the end of the challenge, we want to continue working on this project on our own and then release it onto the website so that everyone can use it and people can build off of it. So then in theory, in the future, people can actually use it and implement it into their daily life. So we don't have yet multiple libraries for just A or B, but that's definitely something we're looking into.
Okay.
Yeah, and through that, having multiple libraries of full alphabets, the program would be able to learn which library the user's input most matched. So it would go to that library first, in theory, once it's implemented.
Right.
Yes?
Yes.
Do you handle things with people have different size hands?
For different size hands, since we've tested out the program for a variety of different people, generally it's just how close you are to the screen, if you kind of match that up.
Okay.
We don't specifically yet have a method that will.
Or if somebody maybe just rotate a little bit?
For rotations, things like that, it generally can detect that it's very similar.
Okay.
But for the thickness of a hand or the shape of a hand, we currently do not have a solution for that.
And a major factor with that is lighting in the room and background noise. The
Background
program,
visual noise.
yeah, the program is not yet very proficient at extracting the hand from the background noise. So in order to have it be accurate, you pretty much have to have a background that's almost one color, because otherwise the contour image doesn't compare, because you have a hand and then you have your plant in the background, and it looks at the library and says there's no plants in these.
It just sees it as one static image rather than plant, computer, person. It can't differentiate between all the things in the background.
And that's exactly why the Kinect would have been a better option.
No.
Except for
Getting back to the Kinect.
yeah.
We have a code that works, which is really cool. The problem is that our library, since it's open source, and I don't mean open source like OpenCV, which is also open source, the library itself is updated about once a year, so it gets pretty old quickly. And we ran into the issue, whereas when you plug the Kinect into an Xbox 360, or you buy one new on the shelf, it has the newest drivers installed onto the device. But when you're using a library that was designed maybe a year ago, it doesn't work. So whereas we have code, I should have thought about that. Right?
It's a beautiful thing.
Actually, the funny thing is that when we were testing it, trying to figure out a way around this, the Kinect worked better on Mac OS X than it did on Windows 8.
Because why not?
I think it's great.
Yeah.
So in theory, the next library should be coming out sometime in July.
July. And when that comes out, the code should work. And we, just looking at the code and making all these assumptions about it, we think it should be able to be about 90% accurate, more or less, which is fantastic.
Just because of its ability to extract the hand from the background.
Yeah.
It's not dependent on, placing a threshold and saying everything above this is white and everything below this is black.
So you're saying your code will work on new Kinects
No, it's not. It's not the Connect itself. It's the open source library of which we have to use for the computer to work with the Connect.
Yeah, the computer's trying to talk to the Connect, and they aren't meshing well because the Connect is updated, fairly more often than the libraries for the processing.
So I have a Connect, but I haven't used it for a long time, so yours won't work on my Connect.
Well, I mean, mine, I had used it like twice a year. I mean, it's pretty old. It simply is just a library. They have to update it to this point, and then it will work. It's nothing about the Connect. It's nothing about like processing the language. It was created 2001, 2002, MIT. It's pretty great. It's nothing about that. It's just simply these libraries that we're waiting on, and then working from there. So in its entirety, processing with the Connect doesn't really work, but it's definitely an aspect of which we will put further research into. I'm just slurring for some reason. So why Connect? I mean, one microphone has status LEDs for troubleshooting, RGB images, 3 microphones, 3 access accelerometer. The Connect, you can actually move it up and down. And with the new release of the libraries we're using, we might actually be able to move the Connect so it can track the person. As the, I mean, I don't know why somebody would be walking around doing fingerspelling, but they could, and that'd be really cool. Why not? And also 3D depth sensing. Point at the photo. That is just as soon as like you open up a few lines of code, like pairing with the Connect and like, just initial startup, that's what I look like in my room to the Connect.
You can't do any contrast tweaking or anything like that. It does all that.
Well, that's where we have to basically figure
Find
out
the hand.
Find the hand and figure out a protocol to have it so it just looks at the hand. There are screen captures of the process that we went through to actually have it so it could recognize the hand, because we were able to successfully extract the hand.
They're on the poster.
But
Should I show the poster?
Yeah, you can show the poster.
Okay. These pictures and these ones up here are the Connect's process for, extracting the hand from a person. It's basically doing 3D depth sensing and then kind of slimming out the area around the hand so that it's recognizable as a hand.
But not
instead
wanting
of
to
just a blob.
like contort it or whatever, like make it look weird. We want it so it's just the hand. Yeah,
Next.
of course.
Alrighty.
Website.
Because I came onto the project in December, one of my main tasks was the website. And basically, I bought the domain name for a year, and I'm probably going to renew it at the end of that period, because we plan to continue this project into the future, because we see it being useful and possible to implement in the real world somehow. Because not only is it useful for ASL gestures, it's also useful potentially for just normal gestures to interact with your computer, like swipes to change programs or scrolling, that kind of stuff.
We also, all of our source codes, we want to do some like screen capture, like video type of deals with the builds as they progress. The image library, basically everything we do will be updated to the website, because we truly want this project. We were not able to recognize all 26 gestures. We only have 6 currently. But we want this project to rather stand as a catalyst for people all across the world who have an idea of, hey, gestural recognition for hands. And to be able to find our site, find our work, find our code, contact us, and build off of it. Because something like this could truly help people who rely on ASL or simply want the feature.
And plus, the research that we did initially, or mainly Noah did originally, was really convoluted. There's not a lot of work on this. So having another resource out there when someone looks up this kind of work would be immensely helpful.
So what's next? It's kind of sad. We want to have, by the end of this month, so like a week, we will hopefully have all 26 of our ASL fingerspelling gestures working for the project. The 6 gestures, those were simply for like the due date of the final report and the code, whereas we've been just continuing our work on it. In the future, once we have everything smoothed out, all the features, everything that we really like, and hopefully have a higher margin of success, we would like to, in theory, see the Python program ported to handheld devices, such as Android, iOS, what have you.
Essentially Siri, but for fingerspelling.
Yeah.
Right.
So, because at its core, this project cuts out the translator. So someone could pull out their phone. There's a deaf person, they're signing, no idea what they say. I'm not sure what the context of the situation would be. But they could pull out their phone, point it at them, and it would tell them what they're saying. And that, to me, and I'm pretty sure to Dimitri, that would be incredible.
Indeed.
Also, for the Python project, also processing, once we get that up and working, we'd like to see about having the graphical user interface, the gestural input, so like clicking and any types of tweaks, or like even moving like different text or just windows. If we could do that just simply by moving the hand, so more fluid motion and bringing things together.
Putting interfacing gestures in place in addition to the fingerspelling, being able to move your gestural space and calibrate that, because right now it's one place in the webcam, and who would want to move their computer when they could move the space that the gestures are in, right?
Yeah. And then, of course, getting the program out there for all. That truly is what we want to do. So, in summation, copied from our final report, we do have a Python program that adequately recognizes, detects, and displays the output of 6 of 26 ASL fingerspelling gestures.
74% accuracy?
Yeah.
Yeah.
We do have code for working with the Connect, but due to driver and library issues, we basically have to wait until things are updated and we can continue, which we definitely want to do. Yeah.
All right. Questions, comments?
I went to ASL.com in review of this, and there wasn't really much there yet. That's pretty much the same?
There's not a whole ton
Okay.
there yet, actually. Yeah.
There's a blog section where I do intend to update our progress from henceforth, getting all 26 gestures up. And as soon as the 26 gesture version of the Python program is up, we will put it live on the website, available for testing.
Also, another thing to mention is for the development of the website, rather than using like templates or things like that, which would really have alleviated some of the problems that we faced, we wanted to just simply design everything ourselves. So everything on the website is custom HTML, and except
So
for
I kind of have.
like the slideshow.
Yeah,
that-
the fingerspelling slideshows are embedded, but I think if we had used a template, there may have been more content.
I was just thinking there might be a code up there.
Yeah. I'm fairly certain that the processing code is up.
The processing code is the Python code. We are waiting until we have all 26 gestures with a high margin of recognition. Then we'll be releasing it.
Okay.
Hopefully end of this month.
Something that's sort of black magic. Have you thought of neural network-based approaches?
We have, but they, rather than for the Python version, I feel as though they would fit more in the lines of the Python/Connect, because the way currently for once you have the hand detection detected and extracted from the rest of the body, That's just simply like graphing out where the fingers would be, like the folds in the hand.
Yeah.
Whereas more of like a neural network solution would alleviate some of the issues, and it would be pretty cool.
Yeah,
A judge that we talked to earlier also suggested projecting a grid into the gestural space and having that be a method of 3D mapping. And that's something else that we're going to investigate.
Yeah, what do you do right now for matching up the ones that you do recognize? What is your technique?
Basically what it is from the web camera, it will take,
Want to show the video?
yeah,
Yeah.
we have a video. Like 2 days ago, Arissa Baca, the woman who helped us at New Mexico School for the Deaf, since they're just this huge campus, they know people all over the world, and I guess she found someone who was interested in our project, and they live someplace in France and speak French. And they took our project and made their own French Sign Language gestures and put them in, because we sent them like the code and then, hey, here's how you would do that if you want to, because ASL probably doesn't mean anything to you. And they did that.
And mind you, he did not change any of the actual code of the project. He just updated the contour libraries.
So this is what it would be. There's no audio.
So the blue square there is the gestural space, and that's the area that is going to be converted to contour.
Also the region of interest, or ROI.
And there's the letter.
Another aspect that we're trying to overcome currently is that the larger the library, if those images are not calibrated and tweaked so they really work well for the program, it cycles very quickly through all the gestures, as you can see. So they just kind of flicker, but that's just simply because it's quickly responding. But if you have a large library of images, there can be issues where it might think that's two different images, or like two different original images from the input. So it will show both of those characters on top of one another. And we're currently looking, as we're expanding our library, as basically how to overcome that. But that's not cool.
Yes?
So, on those kind of contour comparisons, have you looked at ways to kind of reduce the complexity of these contours? There's something called Fourier descriptors. Have you seen this idea?
No.
I haven't.
So you kind of think of the contour as the graph of a function,
Mm-hmm.
and you try to expand that graph into something simple, like a library of sinusoids. So the graph looks like a sine of certain amplitude, certain frequency, plus another sine, and just keeping those 6 or 7 coefficients of the amplitude of the sine, the frequency of the sine would be enough to encode 26 contours.
Oh, so
And
not
also
comparing
they're not
image to
subject to
image.
distance and scale issues.
So you do a 2D FFT on or something?
No,
So-
it's
so instead of-
1D FFT on the contour, because it's a curve.
Mm-hmm.
It's not.
And you can characterize a letter by its first couple of its Fourier coefficients.
Mm-hmm.
And then you take any gesture and get the first couple of its coefficients, and that's what you compare.
Yeah, you're not
So
comparing
essentially-
images, you're just comparing a couple
You
numbers.
just compare the
Okay.
coefficients, yeah.
You have to
That's something we should look
Yeah.
into,
curve,
definitely.
So you know what the curve is.
So instead of directly
Edges,
comparing
edges or
images, you're
something.
comparing mathematical interpretations of
Yeah,
the library and the input?
right.
All right.
They'll probably alleviate a lot of the issues that we're currently having.
Yeah.
Is like if you note, M and N are extremely similar, and S and T extremely similar. And when those are in contour, unless the contour is really tweaked and really messed with for a while,
M
Is
and
there-
N would have the same first couple of.
Sure. Yeah, you might have to go out. I mean, it'd be interesting to see how many coefficients you need
But
to
if they're spelling,
distinguish
if
those.
they're spelling words, you maybe can say, I'm not sure, M or N, and then you can maybe fill in the blank as you
yeah.
figure out what letter.
Like some
what
sort of
word.
predictive text
Yeah.
piece to that? Yeah. All right, we are 20 seconds away from 30 minutes, so.
Thank you very much, guys.
All right. Thank you.